Hey everybody, this is Larry. This is day 14 of the LeetCode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord, and let's look at today's problem. House robber 2. Let me know what you think. Having a house, you chop stash, arranging a circle. Okay. So some of it is that I am familiar with this problem, and so but sometimes that's what practice gets you. And this is a very introductory dynamic programming problem. I'm going to try. I'm going to do it on stream, doing top down first, and then go through the states, and then we could talk about how to write it in a different way. I probably would write it if I was out in a competition, write it in a different way, but I'll show you how to kind of get the intuition for this problem, right? And okay, so and the tricky thing, and maybe some prerequisite, would be just doing House Robber 1, where it is not in a circle. So I recommend you try doing that. I probably have a video somewhere if you search for it, and I would go through that as well. But now knowing that variant, so there really let's say that I'm going to go over it slightly though, where it is not in a circle. If it's not a circle, so okay, so what does this mean, right? That means that if you want to get, like, say do house 2, then you cannot do house 1 or 3, right? And then now we can reduce the problem to just kind of looking at the suffix of the array, where okay, if this is the case, then all that means is that we just have to skip. If we use this, then we skip to look at this suffix, right? And if we don't use this, that means that the 3 is available, so we could use this suffix, right? So this leads to a very straightforward recurrence. Like I said, with dynamic programming, the hard part is often going to be on the formulation and transition. So once you do that, it becomes straightforward, quote unquote, because it's usually like 5 lines of code or something like that, give or take, right? So let's just say, yeah. I'm just trying to figure out what I should name it, but at index, and and I know that we said that we could, you could return this array, another array that would be the suffix, and you could do that. But the common pieces is that we do the index, because the suffix would never change, so then we could just reference it from the original list. So that's kind of one way that we think about it as well. And again, we're kind of ignoring the circular nature of this problem for now, and then we'll go for later. And then the question is, if index is equal to n, that means that we're at the end of the house. Then what does that mean, right? That means that that means that we're not going to make any more money, or whatever the value is. Yeah, money, right? So that's return 0. Of course, we set n is equal to length of the numbers, and otherwise, as we said, okay, so there are only a couple of cases, right? Where, okay, let's say we're at a certain house, this is index. So if we do rob this house, then that means that we cannot rob 1, so the next one has to start from 5. So then we make the decision there. So best is equal to the max of either, or maybe that we'll phrase it another way, which is money robbing house is equal to rob house of index plus 2, because now, this is index plus 1, this is index plus 2, plus the value of robbing this current house, which is nums subindex. And then money not robbing or skipping house, maybe, is equal to rob house index plus 1, right? And then now we just have to return the maximum of money robbing house or money skipping house. And that's pretty much it, if you could believe it. We have to make a small we have to make a small modification, because index plus 2 can be infinite because it goes past n. So let's just make it that. Made that mistake before. Let's go rob house of 0, starting from the first index, right? And this is not going to be right, but at least not in the same way, because it's the circular nature, right? And in this case, it shows immediately, because you want to rob the first house and the last house, which, if it's not circular, it's okay, because they're not related. But because this is circular, the 2 and the 2 matches up together, right? So right now, what I would say is that it matches our expectation of whether it is correct or not. Not to say that this is correct for the current answer, but sometimes you have to verify that the code does what you tell it to do, or what you think you told it to do, right? And that's basically what I have here. So then, well, how do you handle this, right? Well, I think, going back to, let's say our index is at 0, right? Well, what happens? Well, what happens is we could either, again, similar to here, we could either skip the house and we go to the next index. Oh yeah, let's actually do it here. So what happens is that, let's say our index is at 0. We could either skip this house and we just go to index plus 1, which is, skipping this thing. Or we could warp this house and go to index plus 2, right? But then the key thing to note is that if we do warp this, then we cannot warp 10 or the last, the last house, right? So that's basically, from that's all we need to kind of modify the problem, right? And it gets a little bit murky, but in terms of the logic, but that's how we can do, right? So that's it. And there are a couple of ways you can do it. You can actually break this down to 2 functions, each with its own recurrence, and maybe that's easier because at least if you're a beginner, just to kind of separate them, right? And I think that's what maybe I'll do. So this is warp house, except first, maybe. So let's call it that, and we'll have the right suffix, same suffix, because they're 2 different things. And then warp house include first, say, right? And then, okay, so now how do we handle it, right? Well, if index is greater than, not n this time, it's n minus 1, right? Because now if we go here or further, so we ignore the last element, and obviously beyond that, then we return 0. And then now we asked ourselves the same question. If we warp the first house, and these are the same, right? These are all pretty much the same. The only thing that the difference is the index n minus 1. So I'm just going to do some copy and pasting because I'm a little bit lazy. And maybe fixing it. So I would also say at this point, if you have some experience, you can also obviously combine them into one function with some if statements. But I just wanted to make this illustrative. I just want to make it really obvious what I'm doing, right? And then now the kicker, the starting of the function is not right anymore, right? Well, what do we want to do? Well, what happens when we warp the house except for the first? Well, then that means that the money we get is, which is money skipping first house is equal to, why is this in red? That's a little bit weird, but okay, we'll see. Warp house except first, starting from index 1, right? We start the index at 1 because literally the definition is skipping the first. And then now, money warping first house is equal to warp house include first of 0 plus, maybe I have to do this a different way. So 2, right? Plus nums sub 0, right? I just wanted to make sure that it has at least 1, otherwise we're going to make it out of bounds. And the reason why this is the case, and that's why I like to write it like this, is because then you could articulate it in a very English way, right? Well, and that would, you can answer these questions very straightforward from that, which is that, for example, money robbing the first house. Well, you get the money robbing the first house, which is this part. You can point to it, and then you skip the second house, and you go to the third house, which is index 2, right? So this is why you have this index. And that's pretty much it, right? That's, well, you have to return the max of these, obviously. And you can run code again, and it looks good, right? So yay, we're problem solved. Almost. So one thing to note is that n is equal to 100. So that means that if you add n is equal to big and some kind of what did I do? And this is going to be probably, well, it's going to be too slow. A little bit of a spoiler alert is that this will actually end up taking about Fibonacci number of time. So given that this n is equal to, I don't actually know how, I didn't count this one, but let's say it's like 50, it'll be like 1.6 to the 50th power as to how long it would take, which is too slow, especially once it gets to 100. I mean, it's less than 2 to 100, but it's still pretty slow, right? So how will we solve this? How will we fix this? And that's what, I mean, we talked about it with dynamic programming, in this case, memorization. And that's why we have this index here, right? Well, looking at just this one, how many different possible inputs is there to this function? Well, index could go from 0 to n or n plus 1, give or take, depending on how you want to call it, right? So that means that there are only n number of inputs, give or take. And each of them will always give you the same answer, right? So that means that the second time you call it, it will have to give you the same answer as the first time you call it, as the third time you call it, and so forth. And that's when you do something called memorization. And just hand wavy a little bit, you could do the same here and same analysis to get the end time, right? So I'm going to just write a comment. Index can be from 0 to n-ish, maybe n plus 1 if you want to be precise, but ish. And each of these will only make one or two additional calls, a constant number of calls. So each of the function calls will do O of 1 work. So total time will be O of n. And you could basically copy and paste this to here. And and I'm going to implement that now. And now there's 2 DPs. I'm just going to, you can name, I named them actually different things from time to time, but I'm going to, do here where I just call it a cache because that's what I think of it. And it's easier to think about it that way from time to time. But yeah, cache include first is equal to, well, doesn't really matter what this number is, times, I don't know, n-ish, right? N plus 1 maybe to get the n, but it doesn't really matter. And then the other one is cached include first is equal to 4 times n plus 1, right? And then now how we cache it is just, okay, if this index is cached, then we return the result that we already cached. Oops. Otherwise, we do this calculation that you see here, and then we cache it. We put this in a cache. Cache include first index is equal to 2, and then return cache include first index. Right? So this should be good. And then we do a similar thing for except first. And if you're a little bit advanced with Python, you may notice that there are libraries that does this for you. But for the sake of learning, I also always recommend y'all to type this out because then it forces you to analyze the state for time and space complexity. Otherwise, sometimes like I know some people kind of just slap certain libraries, on top and skip the analysis, and then and then I get questions about why things time out even though you cached it. I'm like, well, did you really do the analysis? Yeah. The question sometimes isn't why it doesn't work, but why you think it would work, right? And that's where being strong in the foundations will help you. And if there's still TLZs, that means that if I have a typo somewhere, but that's okay. Yeah, did I miss a typo somewhere? Oh, it's not that I missed a typo somewhere. I forgot to set it as cache, so they never use the cache results. So now we're saying, okay, now that we have the results, we could say the cache is good next time almost. Right. Pretty much instantaneous that time, right? Give or take. So yeah, let's give it a good submit. Hopefully I don't have any edge cases, and there you go. And again, the time complexity, I mean, this is the same, right? So I'm not going to go over it that much, but again, it is O of n for number of cores because that's the number of possible inputs, and each of these does O of 1 work. So in total, it's going to be O of n. Yeah, and in terms of space, as you can see, we do O of n space because you do this way. So, observing opportunity. One is recognizing that this recurrence, these edges that you draw, is very similar to Fibonacci, right? So you can convert it to bottoms up, which I have a video, you could watch it about dynamic programming and progression and doing bottoms up. And then 2 is, again, similar to Fibonacci. If you recognize this, similar to Fibonacci, you'll know that in Fibonacci, you can actually do an O1 space from, like, just keeping track of the last couple of numbers or whatever, right? You can do the same here. So you could do this self in O of n time or one space. I'll leave it up to you as an exercise at home. Let me know what you think. Let me know how you did it. And I will talk to y'all tomorrow. Bye-bye.